What is up, everybody? In our previous video, we took a look at what was an example of a great deep learning paper, and we went from paper straight to implementation in TensorFlow. And I'm, of course, speaking of the implementation of the deep deterministic policy gradients paper. So today we're going to get something slightly different. We're not going to be able to implement any code, but I'm going to show you how to go over papers with a very critical eye. And this is an example of a paper that, in my opinion, would not pass peer review in any really reputable scientific journal. Of course, it's just posted up on the archive, so really anything goes, and that's kind of the norm in deep learning papers. So I want you to see how to approach these things critically so that you don't get taken in by bad information. Let's get started. Okay, so the backstory on this is that I've been contracted to implement this system for a company doing real-time bidding management for a rather large sector of the economy. So it was a company that had around 70 clients and wanted to scale out its operations to managing the accounts of 1,000 businesses, and of course would need automated means for doing so because you really can't have enough manpower to manage 1,000 AdWords accounts. So for those of you who probably don't know what that is, AdWords is actually how Google makes money. AdWords is the bidding system that allows people to place ads on Google search. So when you do a search for something, typically the first several results that pop up will be paid advertisements. And the management of those paid ads is big business, right? It makes Google about $50 billion a year. It's big business for them, but it's big business for those that manage them as well, because there is kind of a black art to managing them, and it is at the very least quite time consuming. So this paper purports to use deep Q learning for managing the real-time bidding problem. So when someone enters a search, there is an auction that goes on, and based on what the advertisers bid as well as the quality of their ads, they are assigned a rank, where of course those with a higher rank are more likely to get clicked and therefore more likely to get a sale. And so this paper talks about real-time bidding for a sponsored search, which is a pretty difficult problem to solve. And so they propose a solution that I think is bunk, and I'm going to go over precisely why. So let's get directly into it. So they basically describe everything I told you about how all of that works. That's the purpose of the introduction, to set the stage and give the reader background information. And I didn't detect anything incorrect in what they said here. Now, one important caveat here is that they're using the Alibaba search engine, whereas my experience has been on Facebook ads and Google search ads. So there may be some slight differences, but I don't think there are significant enough differences to render my analysis moot. So they talk about previous work that has been done, and the main problem with applying reinforcement learning to the bidding problem is that it is not a Markov decision process. So if you recall from our free reinforcement learning course, a Markov decision process is a process in which the current state depends only on the prior state in the action taken by the agent. No other factors such as the history of the system matter, right? It's only a function of the previous state plus action. Well, of course, bidding in a real-time auction is not a Markov decision process, right? Each auction is going to be fundamentally different, because it could be a totally different person behind the keyboard. It could be a totally different time of year, of day. There could be different advertisers. Google will sometimes decide when an advertiser will participate in a particular auction, right, to minimize their amount of ad spend so they can show ads later in the day. There are, in other words, so many factors that go into each individual auction that no individual auction is a Markov decision process. Neither does a chain of them form a Markov decision process. And so this is the problem they seek to address. This kind of renders the application of reinforcement learning to this problem a little bit wonky, because, well, the fundamental assumption of reinforcement learning is violated. So it's difficult to actually apply the techniques. And so they talk about prior work by other people that seek to kind of get around this problem of a Markov decision process. Okay, I understand. Simply because something isn't the case doesn't mean you can't try, and doesn't mean you can't try to find creative solutions. So they set the stage by describing all of this and talk about aggregating data at the hour level. Again, kind of sketchy. We'll get into that more in a minute. So then they go on to talk about related work and reinforcement learning in general. Of course, if you've been a long-time viewer or if you've even watched a few of my videos, you know quite a bit about reinforcement learning. It's pretty much what we said. An agent interacts with an environment, receives a reward in the process, and the algorithms that we employ attempt to help the agent maximize the total expected rewards over time. So in this case, what is the expected reward? Just so we're clear, the goal is not to get a click, right? If you're an advertiser and you're selling something or you're trying to get leads for a business, the goal is not to get a click on your website. The goal is to get a sale, right? Because only clicks don't pay your bills. You need cash coming in, baby. Cash is king. So the reward in this case would be actual monetary transactions, or at worst, perhaps a person submitting a contact me form, contact us form, or something along the lines of a step in the sales process that will ultimately lead to a sale for the business. So they go to talk about a little bit in the history of reinforcement learning to set the stage. We know all of that. They talk about bidding optimization. That's where they get into the point of what I just said, where you got to make money in the ads, and moreover, the ad cost must be less than the revenue generated by the ads. This is pretty basic. If you're spending more on ads than you're making in revenue, you're going to go out of business really, really quick. And if you're managing ads for someone else and doing that, that's going to be a very difficult conversation to have. Oh, why have you spent so much on ads and not generated enough sales? Probably because you're an idiot and you don't know how to manage ads. So they further define the problem more concretely, Andrew Ng, in terms of actual mathematics. They have some relationships here. This is all well and good. So up to now, everything in the paper is fine. When I was reading the paper, I was just kind of nodding my head. Yeah, I know all of this. This is all well and good. Nothing seems funny here. But as you continue to read, when they go into the methodology is when things start to fall apart. So the action space, let's talk about that for a moment. So when you are bidding on ads, you are making a dollar bid amount. So at least in the United States. Obviously in other countries it's denominated in whatever local currency is there. But in the United States you're bidding in dollars. And so dollars are a bit of a discrete amount, but it is a rather large interval, right? You could in principle bid anywhere from a penny all the way up to essentially whatever number you want. Now, of course, people don't bid $1 million on selling $5 widgets, but the action space is still relatively unconstrained, and that poses a problem for deep Q learning right off the bat. So that kind of makes me raise an eyebrow. The reward, that makes sense. Income gained according to a specific action under state S. Now, this on the surface makes sense. However, it leads to a whole host of other issues. So if you've ever bought anything online, you know that typically it is not a one-click and buy affair. It is a journey where you will take, particularly if it's anything other than a trivial object, you will spend time researching, whatever it is you want to buy. And when you make a search, just because you click on something doesn't mean you have an intent to buy. So what that means is, from the advertiser's perspective, that the searcher may click on one or more ads, or they may click on an ad and then go to organic, or an organic link later. So if you are attributing the sale of whatever widget you're selling to the ad, when the searcher or purchaser actually went through a vast journey of clicking on the ad, clicking on organic stuff, maybe going through your social channels, how do you divvy up that reward? That's a very difficult question to answer, and Google has a number of attribution models where they can assign credit partially based on how many clicks or how long between clicks, things like that, but they don't really address that question here. That also caused me to raise an eyebrow. And so the next thing is the episode, where they treat, sorry, you can't read that, they treat one day as an episode. Now, this on its surface kind of seems somewhat reasonable, but what is special about a day? So when you have an episode in a game, the system resets itself to the initial starting state, right? At the termination of the episode, everything goes back to the initial state, right? And moreover, at the end of the episode, no further states occur, right? It's terminal. So defining it as a day also causes me to raise an eyebrow. So what do we have? We have already 3 points in their methodology and three eyebrows raised. So it's kind of off to a rocky start. They go from understanding the essence of advertising and reinforcement learning to making some rather questionable assertions. And Of course, they talk about a policy pi, which maps states to actions, blah, blah, blah. And they talk about more of this stuff. Now, here's where they make one of the biggest blunders. So, well, okay, so maybe the second or third biggest blunder, but they make an assumption. And you know what they say about assumptions, right? So they're quite dangerous to make. And it says, two auctions, auction I and auction J, can be a substitute to each other as they were the same if and only if they meet the following condition, that the squared delta between the two divided by the minimum of the squared terms is less than 0.01. This kind of substitution will not affect the performance of a Markov decision process based control system. So they kind of get this from some other if you look at the references 0, 16, and 28, it looks like they may get this idea from other papers, but I don't know where this is justified. So this is attempting to put a mathematical criteria on something which may or may not be fundamentally mathematical. So if you have an auction, what does it mean for one auction to be the same as another? So if you're thinking about, let's say, an auction house, right, then if I want two auctions to be the same, it means they have to have the same people, same stuff for sale. So saying that two auctions can be a substitute for one another if the if this criteria is met based on the vectors that they choose to describe the auction, seems highly suspect and a very dangerous assumption. Dangerous in the sense that it's probably not justified, because they never put any significant constraints on the vector auction I and auction J. So they use some, we'll get down to the meat of it later, where they show what they consider to be the vectors for auction I and auction J, but in my mind, this is highly suspect. And then they go on to talk about, based upon this assumption, this shaky house of cards, they go on to talk about the robust Markov decision process model. And they say our solution is inspired by a series of regular patterns observed in real data. Okay, so I like that. They're observing real data. That's a really smart thing to do, right? So they get data from Alibaba. I don't know how they have the connections to do so. Getting data from anybody other than your own advertisers under management is pretty much impossible. Nobody wants to share their advertising data, right? Especially Google, because that's how they make their money. If they gave out that data, then you could reverse engineer their algorithm, dominate it, and make $1 billion just by manipulating their ads. It would be very almost trivial. So they get some data and they make some observations based on the temporal correlation. So if we take a look at these plots up here, you see at the top you get second level clicks. So they get a bunch of clicks per second. So it's telling me they are talking about very high volume products. So these are mass consumer goods. Oh, and I need to back up for 1 second. So this was being, I don't want to give too many details, but this paper was being analyzed in reference to applying it in an industry where sales are on the order of tens of thousands of dollars, and they happen infrequently with a very long sales process. Nobody's going to click on something and buy it online, and so the applicability of this to our problem was very questionable. And at the end, I'll talk about a little bit about how this whole thing came to be, but for now I want to get to the problems with the paper. So what they do here is they look at the second level clicks and say, well, okay, these look not at all similar, which I agree, they don't really look all that similar. If you take a look at the plots, looks kind of wonky. Then they take a look at minute level clicks and say, well, there's some waveform looking thing there. That's the middle set of plots here. They say that thing looks kind of like a waveform-ish. And if they aggregate it on the hour level, they get two forms that look kind of similar. Now, they did this 2 days, which is January 28th and January 29th of 2018. So they picked 2 days at the end of January in 2018 and said, oh, look, the hour level data looks pretty similar. Therefore, aggregating at the hour level data solves a problem of the Markov decision process model. So effectively their argument is, since these two look the same, very similar, that we can apply the Markov decision process to reinforcement learning and model and control the stuff with Q learning. So that is highly suspect. So you don't have to be an expert in advertising to think of how that can possibly go wrong, right? If you just pick 2 days at random, what about December 31st and January 1st. Might those 2 days be significantly different? And might aggregating over the hour level between those 2 days pose a problem, right? It's immediately obvious where the limits of this apply. And so if you have industries where these sales are cyclical, where some seasons you sell more than others, then obviously comparing from one day in one season to another day in another season doesn't make any sense. And if you are training a model, in one season and attempt to use it, right, in a later season, how is that going to help you, right? The auctions are totally different, right? The people that bought the stuff earlier aren't going to be looking for it again, right? It's an expensive good that is not readily consumed. So this assumption is an assumption made simply for the sake of generating a paper. Now, I don't know how many days they looked at to get this, and I have seen this data in my own experience as an AdWords account manager. You do see days that look the same, but then you have the next day and it's totally different. You may get a whole bunch of clicks one day, decent amount the next, and then nothing for a week. It's entirely possible, and it's almost entirely unpredictable. You can get a sense of it based on personal experience, but you can't really predict it mathematically. It's a completely random function as far as you're concerned. Certainly there are reasons for everything, but you don't know the fundamental underlying dynamics, so from your perspective, it's freaking random. So then they go on to talk about state transitions where they have states defined as budget, time, and G bar, which is a feature vector containing aggregated statistical features of auctions in the time period. And then they say number of clicks, number of impressions. An impression is every time an ad is shown, so every time somebody searches and they see the ad, that's an impression. Cost, click-through rate, conversion rate, that's whenever somebody takes whatever action you want. It's defined by the advertiser. In the case of probably Alibaba, it's basically a sale. You can think of it. But in other industries, it could just be filling out a lead on a contact form. Pay-per-click. Then they're using this. This raised an eyebrow. It's not technically wrong, but pay-per-click refers to the type of advertising. You would say cost per click, CPC, not pay-per-click. Anyway, so that's a minor issue. So in this way, an episode of this way looks like it. Oh, we obtain an episode with fixed steps and they talk about the state transition probabilities, which of course you need for knowing how you're going to end up in a different state from whatever state you start. And they get this product here. Okay, and it's a product of probability distributions over these aggregate statistics. Okay, fine. Then they make an observation, which I don't know. It's questionable. It says let G sub I sub T be the aggregated value of feature I at step T. When G and the action are fixed, the next aggregate state G I T plus 1 will meet the following terms. So the next feature vectors will vary relatively smoothly with respect to the previous feature vectors. That's what that's saying in real words. So it's proportional. It's belonging to this interval 1 minus eta times G to 1 plus eta, where eta is a small value. So it doesn't vary much between time steps. So in this case, the time steps are hour, because remember, up here they're aggregating at the hour level. And down here, they're making an observation that between each hour level, they don't vary too wildly. And that is not at all the case in the general case. That may be the case in a high volume advertiser with 24/7 advertising. That may be the case, but that's not true in the general case, right? That's highly suspect. And that right away, limits the utility of what they're proposing. And so they say this quantity here, they just, take the square, plug this in, and say, according to assumption 1, we can deem any possible value of G sub I superscript T plus 1 to be the same, which means this probability distribution equals 1. Maybe, okay, according to equation 5, we finally get P of S, A, and S prime equals 1. And it says, this means the state transition is consistent among different days, leading to a robust Markov decision process. Now, this is where everything just falls apart. This is total bullshit. Pardon my language, and I hope YouTube doesn't strike me down for that, but it is just total horseshit, man. This is ridiculous. They're saying, because of this observation made on 2 days, January 28th and 29th, not special days at all, just 2 random days, picked out of thin air for no reasons whatsoever that they're revealing. They get these hourly level plots that look kind of similar, sure, all well and good, but then they say, because of that, this. Because of that, we can apply the robust Markov decision process to different days, and therefore use our fancy schmancy Q-learning method. I don't buy it. This would not pass any critical review. So what do I know about review? I didn't talk about that earlier. I have 5 publications in physics, not in deep learning or machine learning or computer science or anything like that, but in high tier, not the top tier, not nature or science journals, but in high tier physics journals. I've got a couple first author papers and a few second author, third author papers. So I've been through the review process many times, and it is a brutal process. It is cutthroat, where the people reviewing it are your competitors, and so they have every reason to take you down, right? They don't want to see you succeed. Because they know who you are and you don't know who they are, right? So if they're your direct competitor, they know who you are and they're trying to take you down any way they can. So that's just the nature of every competitive endeavor. That's life. So this would not pass any measure of scrutiny. This assumption, even to anybody with any level of common sense, just thinking about the problem for more than 30 seconds would allow. This would be shot down almost immediately. But they continue. They continue. So now they talk about the action space. So this was another problem I had alluded to earlier. So remember, the action space in this case is what bid the agent is going to apply to the auction. The bids can be, any quantity in the interval of 1 penny all the way up. Of course, this is probably a nuance since it's on Alibaba, but they basically solve this problem by inserting a fudge factor alpha times this quantity PCVR, which is the predicted conversion rate. Now, these search engines, Google in particular, I don't know if Google provides something analogous to a predicted conversion rate. I don't recall, actually. But it's a totally meaningless quantity. What does it mean, predicted conversion rate? Predicted by whom? Who's going to predict that, right? It doesn't make any sense. It means nothing. It's an absolutely meaningless quantity. And this quantity alpha is a discrete thing between 1 and 100. And so their bids, their actions are this discrete number alpha, which is what the agent varies, times this predicted conversion rate, which is a meaningless quantity. Now, this solves the problem of going from a continuous to a discrete action space. It does solve that problem, and it would allow you to use deep Q-learning, but it's a totally meaningless solution. A more robust or logical solution would be using historical data, for instance, to say, okay, we know from managing this account that on average it's going to cost us X number of dollars to make a sale, right? And so then you would want to make the action to be some fraction of that quantity, right? Because you don't want to spend more than you're going to get to make a sale, unless you have some advanced system where you can email market to people later and get more sales on the back end. That's kind of an advanced marketing thing. But in general, you wouldn't want to spend more on the ad than you would get on average for a sale. And so that would be a much more meaningful quantity to use. And again, a reviewer would catch this because this is predicted conversion rate. Who predicts it? Google? What the hell does Google know, right? Google, they know a lot, but they don't know anything about conversion rates. I promise you that. I've managed accounts, many tens of thousands of dollars a month in ad spend, and they know nothing about conversion rates unless they have a huge mountain of data. Then they can do a little something to help you out, but beyond that, not happening. Okay, so those are two major issues that the Markov decision process assumption is violated, and having 2 days where the hour level plots look similar doesn't change that fact. It is a totally arbitrary solution to the problem, and I want to see more data. If I were a reviewer, I'd want to see more data. Say, hey, show me, dates that are a month apart. Show me dates that are 1 quarter apart and then 1 year apart, right? If you have that data, you have access to historical data. Show me the data and show me that that's actually valid. Even just 2 weeks apart, right? Show that to me. Maybe it is the case, but in the general case, I don't think so. They should, in a responsibly written paper, constrain the realm of applicability. If it doesn't work in all environments, they need to say this will only work in auctions in which we have the following set of criteria. Okay, that's another huge issue. And the second huge issue is the action space. They do reasonably go from a continuous to a discrete action space, but they use a meaningless quantity to do so. And it's not something that is fundamentally the same over time, right? This number, this predicted conversion rate, can change at any time for any reason that you do not control and you do not know. If you at least used the average lifetime value of a customer, for instance, how much the business knows they're going to make off of a customer, that's something that's relatively constant over time, something they can at least control, right? If they raise their prices, that amount may fluctuate, but that's something they at least control. They at least have insight into how it's calculated, and they know everything they need to know to make an intelligent decision based on the data. Using predicted conversion rate is a black box of the highest order. They don't know anything. So then they go on to the algorithm. Now, the algorithm is pretty typical for deep Q learning. We have seen this 100 times, and the only thing new here is that they have a Q, I believe it's Q episode. They have a Q train, a Q target, and a Q episode. So they introduce a third network. So right away, if you know Q learning, deep Q learning, you know that oftentimes we'll do double Q, deep Q learning, DDQN, and we'll have a target and a train network. And that is to account for the maximization bias inherent in the deep Q learning algorithm. So if you're not familiar with that, what that means is in deep Q learning, you're using the same network to both evaluate the value of an action and to choose that action. Moreover, you're most of the time choosing actions according to a maximum. So you're choosing things that you think are maximum. So you're inherently biasing your estimates, right? And worse off, you're moving the estimates as you go along because you're updating the same network that you're using to estimate the values and to choose actions. So the solution to that is to use two networks, one to learn the values of the actions and one they use for your policy. So it's effectively an off-policy method that uses two networks to solve maximization bias. Now, that's well and good. That is well known. That works well in Atari, works well in a number of environments. That's pretty cool. But this Q episode, so this is an entirely new network. And, the only thing they say is that they introduce it for stability purposes. Now, what does that mean? That to me means that they know their algorithm doesn't really work. It may work on the 2 days that they cherry-picked, but it does not work in the general case. So they introduce a third network that is probably updated over some longer time interval, which is what they say, updated at the end of each episode, which is the end of every day. So they know that at the end of every day, things aren't the same as the next day. Otherwise, the two other networks would be sufficient. So right away, they're admitting, hey, we need to introduce another fudge factor. This is like Ptolemy's circles within circles, right? They've made some silly assumptions, and so now they need to introduce more complexity to account for the aberrations and distortions that occur as a result of their faulty assumptions. And so they call that a Q episode. They update it every day, and that to me is another third or fourth red flag. I have lost count so far. Okay, so next up, they talk about the results, the experimental setup, and this is all just who really cares? So they talk about PCVR, and that's given to them by Alibaba. Who knows how that's calculated? Alibaba probably not going to tell you. They're like any other advertiser. They also talk about a massive agent model. So the point here, this isn't fundamental to the paper. They ask the question, what happens if you have more than one AI agent? And the answer is simple. If you allow them to, they will collude. If you have competition, if you allow multiple agents to communicate in a market, they may very well fix the damn prices. Now, in a human, you have price fixing cartels don't really work because there's a strong incentive. If let's say you have a gas station, you've got a corner with 4 gas stations, and all the gas station owners say, hey, we're going to keep prices within 1 penny of each other, so that way we can all make lots of money. Well, if you're greedy, which everybody's inherently greedy, let's get over that. Greed is a constant in human nature. The greedy person, which we all are, is going to say, hey, these other guys are, setting their prices at, $3, $2.99, $3.01. But if I go $2.95, well, then I'll take all the business, right? And then the other 3 will, they'll be screwed, right? Because they agreed to keep prices the same. It doesn't work, right? Everybody has an incentive to lower the price to attempt to capture business. Cartels inevitably end to price wars, unless there's some threat of state force, keeping it together, as is typically used in the real world. But here we're dealing with artificial intelligence, where basically they say, if we allow the agents to cooperate, they get better results. No kidding, because they collude. That's not difficult to see. Talk about their experimental setup, and they talk about all of this stuff they would typically use, network architectures. That's all well and good that they provide that. That's nice and transparent. I like that. Then they talk about relative performance. Now, this is a totally meaningless quantity because the data is certainly cherry-picked. They've made so many faulty assumptions that I don't trust the data they present at this stage. If I'm a reviewer, I'm reading this critically, I don't think this is accurate. They may not just manufacture the numbers out of thin air, but they probably cherry-pick data sets to use. I think here's where Convergence, they talk about the use of the extra algorithm, but extra network. But at this point, I've kind of tuned out. So that's my analysis of the paper. Now I have to tell you how this came about. So this came about because I was interviewing for a freelancing gig where they were going to implement similar systems in a marketing management tool for high dollar industries. And the person reading the paper didn't have domain expertise in pay-per-click advertising. They didn't come to me first. Why would they? They don't know me. I'm just some Joe Schmo. But someone who did not have domain expertise in it kind of chose this as a first approach. Now, I never got to finishing it because, surprise, surprise, the project was mismanaged. I ended up quitting the gig. I talked about that in a previous video on when to walk away. The employer ended up trying to cut my pay, which is a big no-no. I don't play that game. I walked away and said, go find someone else that has direct expertise with deep reinforcement learning and real-time bidding. Have fun with that. But this was a paper where someone who did not understand how to read something critically was making decisions and recommendations to a CEO. And it's a person who was probably technically competent but had stepped outside the arena of their expertise and tried to pick something that would be cool for a research paper, but wouldn't be cool for managing someone's business. People's livelihoods depend on that. If you spend a bunch of money, a business's money, on freelancers implementing some poor approach to a problem, then, man, that's not cool, man. So that's not how I would have handled things. But nevertheless, I was introduced to this problem, never got it to work. It would never work in the particular industry in which we were attempting to apply it. Could it work in the general case? Maybe. Not in the general case, but in some specific industries and verticals. Could it work? Perhaps. If you have something where the products are perfectly interchangeable and they are consumed on a ready basis, something like, I don't know, razors or paper towels, for instance, toilet paper, something like that, where there isn't a whole lot of difference between them and the margins are pretty slim, then sure, you could probably apply this to those particular verticals. But anything outside of the realm of products where they are interchangeable, cheap, and readily consumed, such that each day is, no different than 343 days before, then outside of that, then you're kind of screwed and you can't really apply it. But that is neither here nor there, so I just wanted to introduce to you the ideas of how to read a paper and to be critical. So to recap, how to be critical. So if you don't have deep expertise in something, then you need to be thinking in terms of statistics. So you don't need to be an expert in pay-per-click advertising to look at 2 days chosen at random and say, gee, does that hold true in the general case? You always want to question, does this hold true in the general case? And that question will guide you towards a chain of logic that will allow you to be critical about the project and allow you to either be a more critical reviewer or to come up with more original and better ideas yourself. Another thing you can do is to question assumptions. So this is important in your own life. Question all of your assumptions always and forever because they're probably wrong, or at least they need to be better thought out. But in this case, questioning this assumption, you don't have to be a genius or know anything about pay-per-click advertising to do. You just have to say, does this really hold true? 2 auctions can be a substitute. Well, even just thinking of an auction in the sense that we all probably think of it, a guy with a gavel saying, going once, going twice, sold to the gentleman in the back. It's hard to see how 2 auctions can be interchangeable. So that assumption is easy to question right off the bat. So if you question that assumption and the assumption that the assumption that that's days separated by weeks, months are going to be interchangeable, then you'll be able to well on your way to formulating critical thinking skills about deep reinforcement learning. Unfortunately, it's the state of the art, as it were, that you have to do this because this stuff gets put up on the archive and there's no peer review there, right? The only peer review is what you do, looking at it and saying, does this make sense? Does this jive with what I already know? Does it jive with basic logic? And in many cases, I know as a grad student we publish on archive the preprints. Those were always prior to the peer review process, so they may have lacked polish. They may have had some points that could have been better shored up. That was the point of peer review, is to say, your chain of logic here is a little iffy. Maybe provide some supporting data or some other statements to clarify, something like that. And so they were not the top quality they could possibly be. They weren't as good as when they were published in physical review letters or applied physics letters or physical review B or whatever. So the papers here are not going to be a final product, and they're not peer reviewed, so you have to be very, very critical to do that. Question assumptions and question assumptions, and just use a chain of logic to determine if something is applicable in the realm in which they are saying. So this has been a bit of a rant, no code here. I just wanted to dive deeper into the process of how you read papers, because I don't think there's a whole lot of information out there on that. And I have a fair amount of experience with it as a grad student, as well as trying to implement stuff in deep learning. Questions, comments, leave them down below. If you found this video helpful, please share it. That helps the channel immensely, and it's free, costs you nothing except a few seconds of your time. And I will see you all in the next video.